Hey there, curious minds. What if I told you that somewhere out there, another version of you is watching this exact video, except they already hit the like button? Welcome to the mind-bending world of parallel universes, where science fiction crashes headfirst into actual physics, and the results are way weirder than anything Hollywood ever dreamed up. We're talking multiple versions of reality, cosmic collisions between universes, and the very real possibility that every decision you've ever made created an entirely new world. No pressure. For centuries, this stuff was reserved for philosophers getting a little too creative after their third glass of wine. But here's where it gets wild. Modern physicists are now finding actual evidence that suggests our universe might not be flying solo. We're seeing strange anomalies in the cosmic background radiation, bizarre quantum experiments that make zero sense unless parallel worlds exist, and mathematics that practically demands an infinite number of realities. The multiverse isn't just science fiction anymore. It's becoming science fact. So before we tumble down this cosmic rabbit hole together, do me a favor. Smash that like button if you're ready to have your entire perception of reality questioned, and drop a comment telling me where you're watching from. I want to know which version of Earth is tuning in tonight. Are you ready to discover that you might not be as unique as you thought? Let's dive in. The idea that we might not be alone in the cosmos, not just as a species but as an entire universe, didn't start in some high-tech laboratory with scientists in white coats staring at complicated equations. No, this mind-bending concept was born thousands of years ago in the minds of ancient philosophers who had nothing but their brains, some olive oil, and way too much free time. And honestly, they got surprisingly close to what modern physics is now suggesting. So let's take a journey through time and trace how humanity went from, what if there are other worlds, to, wait, there might actually be other worlds, and we have math to prove it. Our story begins in ancient Greece, around the 5th century BCE, with a group of thinkers called the atomists. Now, these weren't your typical philosophers sitting around debating whether a chair is really a chair. These guys, Leucippus and his student Democritus, proposed something radical. They suggested that everything in existence was made up of tiny, indivisible particles called atoms, and that these atoms existed in an infinite void. But here's where it gets interesting. If the void is infinite, and atoms are constantly moving and combining in random ways, then logically, every possible combination of atoms must exist somewhere, including, yes, other worlds, other Earths, maybe even other versions of you, except that version actually remembered to call their mother on her birthday. Democritus didn't just hint at this, he stated it outright. In an infinite universe, there must be infinite worlds, some similar to ours, some completely different. Not bad for a guy who lived 2.5 millennia before Netflix started making multiverse movies. But ancient Greece wasn't done blowing minds. Enter Epicurus, another philosopher who took the atomist ideas and ran with them like he was training for the philosophical Olympics. Epicurus argued that in an infinite universe with infinite atoms, it would be mathematically absurd for our world to be unique. There had to be countless other worlds out there, some inhabited, some barren, all existing simultaneously in the vast cosmic void. His follower, the Roman poet Lucretius, later wrote an entire poem about this called On the Nature of Things, which is essentially a 7,400-line argument for why the universe is way bigger and weirder than anyone wanted to admit. Unfortunately for Lucretius, his timing was terrible. The poem was largely forgotten for over 1,000 years because apparently humanity decided it had better things to do than contemplate infinite realities. Like, survive plagues and fight over land. Now, here's where things get a bit darker. For most of recorded history, suggesting that there might be other worlds out there wasn't just philosophically edgy, it was potentially fatal. The medieval church had a very specific view of the cosmos. Earth was the center of everything, created by God for humanity, and that was that. Suggesting otherwise was heresy, and heresy had some rather unpleasant consequences involving fire and public gatherings you definitely didn't want to attend. So for centuries, the idea of multiple worlds stayed underground, whispered about in academic circles but never spoken too loudly. After all, it's hard to develop groundbreaking cosmological theories when the punishment for being wrong is being burned at the stake. Not exactly an environment that encourages creative thinking. But some people just couldn't keep quiet. Enter Giordano Bruno, a 16th century Italian friar who looked at the church's cosmology and basically said, "Thanks, but I'll pass." Bruno was a Dominican monk who somehow managed to get himself excommunicated from pretty much every religious. institution in Europe, which is actually impressive if you think about it. The Catholics kicked him out. The Calvinists kicked him out. The Lutherans kicked him out. The man was collecting religious rejections like they were stamps. But Bruno didn't care. He was too busy revolutionizing how humanity thought about the universe. Building on the work of Copernicus, who had recently suggested that Earth revolved around the sun rather than the other way around, Bruno took things several steps further. He proposed that the sun was just another star, that the universe was infinite, and that it contained countless other worlds, many of which might be inhabited by their own life forms. This wasn't just astronomy. This was a complete reimagining of humanity's place in existence. Bruno wrote extensively about these ideas, traveling across Europe and teaching anyone who would listen. He envisioned a cosmos teeming with life, with infinite suns and infinite planets scattered across an infinite void. Each star, he argued, might have its own planetary system, its own worlds, its own beings looking up at their night sky and wondering if they were alone. It was beautiful, it was revolutionary, it was also extremely dangerous. In 1600, after years of trials and imprisonment, Bruno was burned at the stake in Rome for his heretical beliefs. The church wanted to make an example of him, and they certainly did, just not in the way they intended. Bruno became a martyr for free thought, a symbol of the human spirit's refusal to accept comfortable lies over uncomfortable truths. He died for suggesting that the universe was bigger than we could imagine, and 4 centuries later, science is proving him right. After Bruno's execution, you might think people would be a bit more careful about proposing radical cosmological ideas, and for a while, they were. But science has this annoying habit of refusing to stay quiet, and by the 17th and 18th centuries, the idea of multiple worlds was creeping back into intellectual discourse. Philosophers like Gottfried Wilhelm Leibniz played with the concept, though in a slightly different form. Leibniz is famous for proposing that we live in the best of all possible worlds, which sounds optimistic until you realize it implies that other possible worlds exist, even if they're somehow inferior to ours. It's like being told you got the best room in the hotel, which raises the question of what the other rooms must be like. Leibniz wasn't talking about physical parallel universes in the way modern physicists do, but he was laying the philosophical groundwork for thinking about reality as one possibility among many. The 19th century brought even more fuel to the multiverse fire, though most people didn't realize it at the time. The development of non-Euclidean geometry, mathematics that described spaces with different rules than the flat geometry we learn in school, opened up new ways of thinking about dimensions and reality. If space could curve, if parallel lines could meet, if the very fabric of existence could bend and warp in ways our intuitions couldn't grasp, then who was to say there weren't other spaces, other dimensions, existing alongside our own? It was still largely theoretical, but the mathematical tools for describing alternate realities were being forged. Then came the 20th century, and everything changed. The year 1905 saw a young patent clerk named Albert Einstein publish his theory of special relativity, fundamentally altering our understanding of space, time, and the relationship between them. 10 years later, his general theory of relativity described gravity not as a force, but as a curvature of space-time itself. Suddenly, the universe wasn't a static stage on which events played out. It was a dynamic, flexible fabric that could stretch, compress, and bend. Einstein's equations opened up possibilities that even he found disturbing, including the theoretical existence of wormholes, shortcuts through space-time that might connect distant regions of the universe or, theoretically, different universes entirely. Einstein himself wasn't particularly fond of these implications, preferring a more orderly cosmos. But the mathematics didn't care about his preferences. The equations suggested that reality was far stranger than anyone had assumed. But the real multiverse revolution came from an unlikely source: the bizarre world of quantum mechanics. In the early 20th century, physicists were struggling to understand the behavior of subatomic particles, and what they found defied all common sense. Particles seemed to exist in multiple states simultaneously until they were observed, at which point they collapsed into a single definite state. The famous thought experiment of Schrödinger's cat illustrated this absurdity. A cat in a box could theoretically be both alive and dead at the same time, existing in a superposition of states until someone opened the box and looked. This wasn't philosophy anymore. This was experimental physics, and it was deeply weird. The dominant explanation, called the Copenhagen interpretation, basically said that the act of observation caused the wave function to collapse, determining which state the particle would be in. But this raised uncomfortable questions. What counts as an observation? Why does looking at something change it? And what happens to all those other possible states that didn't become real? Enter Hugh Everett III, a young physicist who looked at quantum mechanics and said, "What if we're thinking about this all wrong?" In 1957, Everett proposed what he called the relative state formulation, which would later become known as many worlds interpretation. His idea was elegantly simple, if mind-bendingly strange. What if the wave function never actually collapses? What if, instead of one outcome becoming real and all others disappearing, every possible outcome actually occurs, but in separate, branching universes? When you open the box to check on Schrödinger's cat, you don't determine whether it's alive or dead. Both happen. The universe splits, creating one branch where the cat is alive and another where it's dead. And you, the observer, also split, with one version of you seeing a living cat and another version seeing a deceased one. Neither knows the other exists. Both are equally real. If you think this sounds absolutely insane, you're in good company. Everett's thesis advisor, the legendary physicist John Wheeler, supported the work but was cautious about how it would be received. And indeed, the physics community largely ignored Everett's ideas for decades. The Copenhagen interpretation was established, comfortable, and didn't require anyone to believe in infinite branching realities. Everett, discouraged by the reception of his work, left academic physics and went into defense research, where he could at least get paid well to be ignored. He died in 1982, never seeing his ideas gain the recognition they deserved. But science has a way of resurrecting good ideas, and by the 1970s and 1980s, physicists were taking another look at many worlds. Prominent scientists like Bryce DeWitt championed the interpretation, and gradually it went from fringe theory to legitimate contender for explaining quantum mechanics. Today, polls of physicists show that many worlds is one of the most popular interpretations, with some surveys suggesting it might even be the favorite among quantum cosmologists. But Everett's quantum multiverse is just one flavor of parallel reality. In the late 20th and early 21st centuries, other types of multiverse theories emerged from completely different areas of physics. The development of inflationary cosmology in the 1980s, pioneered by physicists like Alan Guth, suggested that the rapid expansion of the early universe might never have truly stopped. If inflation is eternal, then different regions of space could continuously spawn new, bubble universes, each with its own properties, possibly even its own laws of physics. Our observable universe would be just one bubble in an infinite cosmic foam, with countless other bubbles existing beyond our cosmic horizon. We'd never be able to see or interact with them, but they'd be just as real as our own reality. And then there's string theory, the ambitious attempt to unify all of physics into a single framework. String theory requires extra dimensions of space beyond the three we experience. Dimensions that might be curled up too small to detect, or might extend into vast parallel branes, membrane-like structures floating in a higher dimensional space. Our universe might exist on one brane, while other universes exist on parallel branes, separated from us by a dimension we can't perceive. Occasionally, these branes might collide, potentially causing events as dramatic as the Big Bang itself. It's like living in a two-dimensional world on a piece of paper, never suspecting that there's another piece of paper hovering just millimeters away in a direction you can't point to. One of the most vocal modern proponents of multiverse theory is Max Tegmark, a Swedish-American cosmologist who has categorized the various multiverse proposals into a hierarchy of levels. His level 1 multiverse is simply the infinite space beyond our cosmic horizon, where the same laws of physics apply, but different initial conditions lead to different outcomes. His level 2 multiverse includes the bubble universes of eternal inflation, each potentially with different physical constants. Level 3 corresponds to Everett's many worlds interpretation, where quantum branching creates parallel realities. And level 4, the most radical, suggests that any mathematically possible structure exists as a physical reality somewhere. It's multiverses all the way down, or up, or sideways, depending on which dimension you're counting. What's remarkable about this journey from ancient Greek philosophers to modern theoretical physicists is how the core question has remained the same. Is our reality unique, or is it one of many? The ancient atomists asked it while staring at the Mediterranean sky. Bruno asked it while facing execution. Everett asked it while scribbling equations in his Princeton office. And today, physicists ask it while analyzing data from particle accelerators and space telescopes. The tools have changed, the stakes have changed, But the fundamental human curiosity driving the question hasn't changed at all. The difference now is that we might actually be able to answer it. For most of history, the multiverse was pure speculation, interesting to think about but impossible to test. That's changing. Physicists are now looking for observable signatures that might confirm or rule out various multiverse theories. They're searching for patterns in the cosmic microwave background radiation that might indicate collisions with other bubble universes. They're probing the limits of quantum mechanics to see if many worlds makes predictions that differ from other interpretations. They're smashing particles together at unprecedented energies to look for signs of extra dimensions. The multiverse is no longer just philosophy. It's becoming experimental science. And this is where our story really gets exciting. Because if the scientists are right, if the evidence continues to accumulate, then we might be on the verge of the greatest paradigm shift in human history. Copernicus showed us that Earth isn't the center of the solar system. Darwin showed us that humans aren't separate from the rest of life. Einstein showed us that space and time aren't absolute. And the multiverse might show us that our entire universe isn't even unique, that we're just one possibility among an infinity of possibilities, one story among an infinity of stories. It's humbling, it's terrifying, and it's absolutely fascinating. So the next time someone tells you that thinking about parallel universes is just science fiction, just escapist fantasy, just wasting time that could be spent on practical things, remember the journey we just traced. Remember that Democritus had this idea 2,500 years ago. Remember that Bruno died for it. Remember that Everett was ignored for proposing it. And remember that right now, today, some of the smartest people on the planet are dedicating their careers to finding out if it's true. The multiverse isn't just a cool concept for movies and TV shows. It's one of the deepest questions humanity has ever asked. Are we alone in existence? Or is existence itself far vaster than we ever dared to dream? Now that we've traced the intellectual history of the multiverse idea, let's get into something that will genuinely make your brain hurt. And I mean that in the best possible way. We're about to explore a concept so counterintuitive, so mathematically elegant, and so deeply unsettling that even physicists who work with it daily sometimes have to stop and stare at the wall for a few minutes. We're talking about infinity. Not the poetic infinity of love songs and greeting cards, but the cold, hard, mathematical infinity of space itself. And here's the kicker. If the universe is truly infinite, then somewhere out there, there's an exact copy of you. Not a similar version, not a close approximation, an atom for atom, thought for thought, identical duplicate. And that's not science fiction. That's just math. Let's start with a simple question. How big is the universe? Now this seems like it should have a straightforward answer, but naturally, nothing in cosmology is ever straightforward. When physicists talk about the universe, they often mean the observable universe, the region of space from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. This observable universe is roughly 93 billion light-years in diameter, which is already incomprehensibly huge. If you tried to drive across it at highway speeds, you'd need approximately, well, let's just say your grandchildren's grandchildren's grandchildren would still be nowhere close. Actually, the sun would burn out, the Milky Way would collide with Andromeda, and the universe itself would approach heat death before you'd make meaningful progress. So pack a lunch. But here's the thing. The observable universe is almost certainly not the whole universe. It's just the part we can see. Beyond our cosmic horizon, there's more space. How much more? Current observations and theoretical models suggest that the universe might be flat, meaning it extends infinitely in all directions without curving back on itself. If this is true, and most cosmologists think it probably is, then we're not living in a very large universe. We're living in an infinite one. And infinity changes everything. To understand why infinity leads to cosmic duplicates, we need to think about how matter can be arranged. The universe is made of particles, quarks, electrons, photons, and so on. In any given region of space, these particles can only be arranged in a finite number of ways. Sure, that number is astronomically large, but it's still finite. Think of it like a cosmic game of Lego. You have a huge but limited number of blocks, and they can only fit together in certain configurations. If you have infinite space to work with, and you keep building random Lego structures forever, eventually you're going to repeat yourself. You have to. There are only so many possible structures, and infinity is a lot bigger than so many. Now let's apply this to the universe. Within the observable universe, there are approximately 10 to the power of 80 particles. That's a 1 followed by 80 zeros. It's a number so large that writing it out would be pointless. You'd run out of paper, ink, and patience long before you finished. But here's the crucial point. Even though this number is absurdly huge, it's still finite. And if you have finite particles that can be arranged in finite ways within a finite volume, you end up with a finite number of possible configurations. Estimates suggest that the number of possible quantum states for the observable universe is something like 10 to the power of 10 to the power of 122. Your eyes probably just glazed over, and honestly, that's a reasonable response. This number is so large that calling it astronomical is like calling the ocean damp. It's technically accurate, but completely fails to convey the scale. But infinity doesn't care about large numbers. Infinity eats large numbers for breakfast and asks for seconds. If space extends infinitely, then there are infinite regions the size of our observable universe scattered throughout existence. And if there are infinite such regions, and only a finite number of possible configurations, then every possible configuration must occur, not just once, infinite times, including the exact configuration of our observable universe, including the exact configuration of Earth, including the exact configuration of you, sitting wherever you're sitting right now, watching this video, perhaps questioning your life choices. Let's put some numbers on this, because the specific distances involved are genuinely mind-melting. Cosmologist Max Tegmark calculated the approximate distance to your nearest identical copy. Now brace yourself, because this number is going to hurt. The nearest doppelganger of you, an exact atomic duplicate living an exactly identical life, would be located approximately 10 to the power of 10 to the power of 29 meters away. To give you a sense of scale, the observable universe is about 10 to the power of 26 meters across. So your cosmic twin is much, much farther than the edge of everything we can observe. You'd need to write a number with more digits than there are atoms in the observable universe to express this distance in meters. It's so far that light from your duplicate's location will never reach us, no matter how long the universe exists. You and your twin will never meet, never communicate, never even know about each other. Which is probably for the best, honestly. Imagine the awkwardness of that Thanksgiving dinner. But wait, it gets weirder. At even greater distances, there would be regions where your duplicate made slightly different choices. Maybe they picked a different career. Maybe they said yes when you said no, or zigged when you zagged. Every possible variation of your life would be playing out somewhere in the infinite cosmos. There's a version of you who became an astronaut. There's a version who learned to play the violin. There's a version who actually finished reading that novel they started 3 years ago. All of them are equally real, equally conscious, equally convinced that they're the real version. The mathematics doesn't distinguish between original and copy because, in an infinite universe, the concept of original becomes meaningless. You're all just different instances of the same pattern, repeated across the endless expanse of space. Now, I know what some of you are thinking. This is ridiculous. Just because the math says it could happen doesn't mean it actually happens. And you raise a fair point. There's an important distinction between mathematical possibility and physical reality. But here's the thing. The mathematics isn't some abstract game detached from the real world. It's based on our best understanding of cosmology and quantum mechanics. If space is infinite and matter is finite, repetition isn't just possible, it's inevitable. It's not a matter of probability, it's a matter of certainty. In an infinite space, everything that can happen does happen, and it happens infinite times. This leads to some truly bizarre philosophical implications. What does personal identity mean if there are infinite copies of you? What does uniqueness mean? What does free will mean if every possible choice you could make is being made by some version of you somewhere? These aren't just idle philosophical puzzles. They're questions that naturally arise from taking modern cosmology seriously. And unlike the ancient philosophers who first pondered multiple worlds, we have mathematical frameworks and observational evidence that suggest these questions aren't just abstract speculation. They might be descriptions of actual reality. Some physicists find this deeply uncomfortable. Others find it exhilarating. And some, like Tegmark himself, have embraced it wholeheartedly, arguing that this level 1 multiverse of infinite space is actually the most conservative version of the multiverse. It doesn't require any new physics, just the straightforward application of existing theories to infinite scales. If you believe that space is infinite, and that the laws of physics are the same everywhere, you've already accepted the existence of your cosmic duplicates, whether you realize it or not. Welcome to the club. We don't have t-shirts yet, but we're working on it. Of course, there are ways out of this conclusion. Maybe space isn't actually infinite. Maybe it curves back on itself in some higher dimensional topology we haven't detected. Maybe there are constraints on particle configurations we don't yet understand. These are all possibilities, and future observations might reveal that our universe is finite after all. But current data leans toward flatness and infinity. And as long as that's our best model, we have to take its implications seriously. Even when those implications include the existence of your identical twin, reading this exact sentence in a galaxy unimaginably far away. Now let's shift gears from the purely theoretical to something we can actually observe. Because here's where the multiverse story gets really exciting. We might already have evidence that other universes exist. Not definitive proof, not a smoking gun, but tantalizing hints written across the entire sky. We're talking about the cosmic microwave background radiation, the oldest light in the universe, and the strange anomalies hidden within it that some scientists believe could be scars from cosmic collisions, places where our universe literally bumped into another one. The cosmic microwave background, or CMB for short, is basically the universe's baby photo. It's radiation left over from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that, the universe was a dense, opaque fog of plasma, with photons constantly scattering off free electrons. Once atoms formed, the photons were released, and they've been traveling through space ever since, gradually cooling as the universe expanded. Today, this ancient light fills all of space as a faint microwave glow with a temperature of about 2.7 degrees above absolute zero. It's everywhere, in every direction, the thermal afterglow of creation itself. When scientists first measured the CMB in detail using satellites like COBE in the 1990s, they found something remarkable. It was almost perfectly uniform. In every direction they looked, the temperature was essentially the same, varying by only about 1 part in 100,000. This uniformity was actually a puzzle in itself. How could regions of space that had never been in contact with each other have the exact same temperature? The answer, inflation theory, proposed that the early universe underwent a brief period of exponential expansion, smoothing out any irregularities and explaining the uniformity we observe. But the tiny variations that remained, those 1 in 100,000 fluctuations, turned out to be gold mines of information. They represent the quantum fluctuations from the early universe, stretched to cosmic scales, and they seeded the formation of galaxies and large-scale structure we see today. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, to map these tiny fluctuations with unprecedented precision. And WMAP delivered beautifully, producing detailed maps of the CMB that confirmed many predictions of inflationary cosmology and helped pin down key cosmological parameters. But WMAP also revealed something unexpected: anomalies, patterns in the data that didn't quite fit the standard model. Regions of the sky that were too cold, too hot, or organized in ways that seemed statistically unlikely. At first, scientists assumed these were instrumental artifacts, or statistical flukes. But as the data accumulated, some anomalies refused to go away. The European Space Agency's Planck satellite, launched in 2009, provided even more detailed maps of the CMB, and the anomalies persisted. One of the most famous is the so-called cold spot, a region in the southern sky about 5 degrees across, roughly 10 times the apparent diameter of the full moon, that is significantly colder than the surrounding cosmic background. It's not just slightly colder, it's cold enough to be statistically weird. The standard cosmological model predicts temperature fluctuations following certain patterns, and the cold spot is an outlier. It's like finding one person at a party who's 3 feet taller than everyone else. Technically possible, but unusual enough to demand an explanation. Several hypotheses have been proposed to explain the cold spot. One possibility is that it's simply a statistical fluke. In a universe with millions of data points, some extreme values are expected. Maybe the cold spot is just the cosmological equivalent of someone rolling 10 sixes in a row. Unlikely, but not impossible. Another explanation involves cosmic voids, vast regions of space with fewer galaxies than average. If the cold spot lies behind such a supervoid, light passing through it would lose slightly more energy than usual, making the region appear colder. Astronomers have searched for evidence of such a void, and some studies have found candidates, though the results are controversial. The void would need to be unusually large and empty to account for the observed temperature deficit, and not everyone is convinced the evidence supports this. But there's a third explanation, and it's the one that makes multiverse enthusiasts sit up straight in their chairs. What if the cold spot is a bruise left by a collision with another universe? This might sound like pure science fiction, but it's a legitimate scientific hypothesis that follows from certain versions of inflationary cosmology. Remember, eternal inflation suggests that our universe is just one bubble in a cosmic foam, with other bubble universes constantly forming nearby. If two bubbles collide, the collision would leave an imprint, a region where the properties of space were slightly altered by the interaction. In our universe, this would show up as an anomaly in the cosmic microwave background. A cold spot, perhaps, or a hot spot, or a region with unusual properties that stands out from the cosmic average. Theoretical physicists have worked out what such a collision signature might look like. It would likely be circular or ring-shaped, corresponding to the intersection of two bubble universes. It might have distinct temperature profiles, with sharp edges rather than gradual transitions. And it would be stable across different observations and frequencies, ruling out instrumental artifacts. The cold spot doesn't perfectly match all these predictions, but it doesn't definitively rule them out either. Some researchers have looked for circular patterns in the CMB that might indicate bubble collisions, and while initial claims of detection haven't been confirmed, the search continues. Beyond the cold spot, other CMB anomalies have attracted attention. There's an apparent asymmetry in the fluctuations. One hemisphere of the sky seems to have slightly stronger variations than the other, which shouldn't happen if the universe is truly uniform on large scales. There's also an apparent alignment between certain large-scale patterns in the CMB and the orientation of our solar system, which some have whimsically called the axis of evil, because it seems to violate the cosmological principle that no direction in space is special. These anomalies could be statistical flukes, artifacts of our data analysis, or hints of new physics. Or, as some theorists have proposed, they could be evidence that our universe is not alone, that other universes exist and have left their marks on our cosmic background. It's important to be clear about the state of the evidence here. We do not have proof that other universes exist. The CMB anomalies are intriguing, but they have multiple possible explanations, and the multiverse hypothesis is just one of them. Most cosmologists would say that conventional explanations, statistical flukes, supervoids, unmodeled foreground effects, are more likely than cosmic collisions. The burden of proof for claiming evidence of other universes is extremely high, and we're not there yet. But the fact that we're even looking is remarkable. A century ago, the multiverse was pure philosophy. Today, we have satellites mapping the sky, looking for evidence of cosmic neighbors. That's progress, even if the jury is still out. What makes the CMB so exciting for multiverse research is that it provides a potential window into physics beyond our observable universe. Most multiverse theories predict that other universes are forever beyond our reach. We can't see them, visit them, or communicate with them. But if universes can collide, those collisions might leave detectable traces. The CMB is like a cosmic fossil record, preserving information about conditions in the early universe. If another universe touched ours during that early epoch, the CMB might remember. It's not a guarantee, and it's not easy to distinguish a multiverse signal from noise, but it's a genuine scientific opportunity that didn't exist a few decades ago. The Planck satellite has completed its mission, but future experiments promise even more detailed measurements of the CMB. Ground-based observatories and balloon experiments are mapping the polarization of the cosmic background, looking for patterns that could reveal new information about inflation and potentially about multiverse physics. The Simons Observatory in Chile and the upcoming CMBS-4 experiment will push the boundaries of what we can detect, potentially either confirming or ruling out some collision scenarios. If we do find unambiguous evidence of a universe collision, it would be one of the most profound discoveries in the history of science. If we don't, well, at least we'll have learned something about the limits of what the CMB can tell us. For now, the cold spot and other anomalies remain mysteries. They could be clues to the existence of parallel universes, or they could be reminders that the cosmos still has secrets we haven't unraveled. Either way, they represent the cutting edge of cosmological research, the place where theory meets observation, and where the wildest ideas face the ultimate test: confrontation with reality. In the next chapters, we'll explore other avenues for investigating the multiverse, from the physics of cosmic inflation to the mind-bending experiments at particle accelerators. But the CMB will always hold a special place in this story. It's the oldest evidence we have, the closest thing to a baby picture of the universe, and it might, just might, contain whispers from beyond our cosmic bubble. We've talked about infinite space creating duplicate versions of you across unimaginable distances. We've explored the tantalizing hints in the cosmic microwave background that might, just might, be scars from universe collisions. But now we're going to dive into one of the most mind-bending mechanisms for generating parallel universes ever conceived by physicists. It's called eternal inflation, and if it's correct, our entire universe is just one tiny bubble floating in an infinite ocean of cosmic foam, with new universes popping into existence every moment, each potentially operating under completely different laws of physics. Grab your floaties, because we're going deep. To understand eternal inflation, we first need to understand regular inflation. No, not the economic kind that makes your grocery bill depressing. Cosmic inflation. The theory that the early universe underwent an incredibly brief but incredibly violent period of expansion. We're talking about the universe growing from something smaller than an atom to something larger than the current observable universe in a fraction of a second. Specifically, in about 10 to the minus 36 seconds. That's a decimal point followed by 35 zeros and then a 1. If you blinked, you missed it by about a trillion blinks. This wasn't gradual expansion. This was the universe putting on a sprint that would make light itself feel inadequate. Inflation was proposed in 1980 by physicist Alan Guth, who was trying to solve some nagging problems with the standard Big Bang model. One problem was the horizon problem. Why does the cosmic microwave background look so uniform in every direction, even though regions on opposite sides of the sky have never been in contact? They've never had time to exchange information or energy, so why are they at the same temperature? It's like finding out that people on opposite sides of Earth, who've never communicated, all decided to wear the same outfit on the same day. Suspicious, right? Inflation solves this by proposing that those regions were once in contact, in a tiny pre-inflationary patch, and then inflation stretched that tiny uniform region to cosmic scales. Problem solved. Or at least, problem elegantly swept under an exponentially expanding rug. Another problem was the flatness problem. Why is the geometry of the universe so precisely flat? General relativity allows for curved universes. Space could bend inward like a sphere or outward like a saddle. But observations show our universe is flat to an extraordinary precision. This requires an incredible fine-tuning of initial conditions, which makes physicists uncomfortable. They prefer explanations that don't rely on the universe winning the cosmic lottery on its first try. Inflation helps here too, because exponential expansion flattens any initial curvature, like a balloon being blown up to enormous size. Even if the original patch was curved, by the time inflation finished, it would appear flat to any observers inside. So far, so good. Inflation solves important problems and makes predictions that have been confirmed by observations of the cosmic microwave background. The tiny fluctuations we see in the CMB match beautifully with what inflationary models predict. Most cosmologists accept that some form of inflation probably happened. But here's where things get weird. The mechanism that drives inflation, a hypothetical field called the inflaton, has a peculiar property. In most regions of space, the inflaton field eventually decays, inflation ends, and you get a hot, Big Bang-type universe like ours. But quantum mechanics means there's always some probability that inflation continues in some regions, even as it ends in others. And in an exponentially expanding space, even a small probability adds up. Imagine inflation as a foam forming in a pot of boiling water. Bubbles form, expand, and eventually pop. But in eternal inflation, the pot is infinite, and the water keeps boiling forever. Bubbles keep forming. Each bubble is a universe, and the foam between bubbles keeps expanding and producing more bubbles. Our universe is one such bubble, a region where inflation ended and ordinary physics took over. But beyond our bubble, in the eternally inflating space, new bubbles are constantly forming. Each bubble is causally disconnected from the others. They can never communicate or interact, except possibly through those cosmic collision signatures we discussed earlier. The bubble universes aren't lined up like apartments in a building. They're scattered through an ever-expanding inflationary space, forever isolated from one another. This picture, called eternal inflation, was developed by physicists including Andrei Linde, Alexander Vilenkin, and others in the 1980s and 1990s. It wasn't what anyone was looking for. It emerged naturally from taking inflationary dynamics seriously. The equations didn't care whether physicists found the implications comfortable. They just kept churning out an infinite number of bubble universes, whether anyone wanted them or not. Unsurprisingly, not everyone was thrilled. An infinite multiverse is hard to test and raises philosophical questions that some scientists would prefer to avoid. But the mathematics is robust, and many theorists have concluded that if inflation happened at all, eternal inflation is probably unavoidable. Now, here's where it gets really wild. Each bubble universe might not just be a copy of our universe with different starting conditions. Each bubble might have completely different laws of physics. The constants that govern our reality, the strength of gravity, the mass of the electron, the fine structure constant, might take different values in different bubbles. Some bubbles might have more or fewer dimensions than ours. Some might have different fundamental particles entirely. Some might have physics so bizarre that matter as we know it couldn't exist, let alone life. Our universe, with its specific set of constants that happen to allow for stars, planets, and people wondering about parallel universes, would be just one possibility among an infinite variety. This connects to something called the string theory landscape. String theory, the leading candidate for a theory of everything, requires extra dimensions and allows for an astronomical number of possible configurations. Estimates suggest something like 10 to the power of 500 different ways to set up the physics. That's not a typo. It's a number so large that if you wrote one possibility on each atom in the observable universe, you wouldn't even scratch the surface. Each configuration corresponds to a different set of physical laws, a different universe. Eternal inflation provides a mechanism for realizing all these possibilities. Each bubble could sample a different configuration from the string theory landscape, creating a multiverse of breathtaking diversity. Some physicists find this beautiful. It explains why our universe seems so finely tuned for life. It's not that someone carefully dialed in the constants. It's that every possible set of constants exists somewhere, and we naturally find ourselves in a bubble compatible with our existence. This is the anthropic principle in action. We observe a universe suitable for observers because unsuitable universes contain no one to observe them. It's like asking why you happen to be born on a planet with breathable air. The answer isn't that some cosmic designer arranged it for you. It's that you couldn't be asking the question if you'd been born in a vacuum. Selection effects explain what looks like design. Other physicists find this deeply unsatisfying, even unscientific. If anything goes somewhere, how do you make predictions? How do you test a theory that says everything happens? These are legitimate concerns, and they've sparked heated debates in the physics community. Some argue that eternal inflation makes string theory unfalsifiable. If any outcome is realized somewhere, you can't rule out the theory by observation. Others counter that the multiverse does make statistical predictions about what typical observers should see, and our universe is consistent with those predictions. The debate continues, and it's far from settled. What's remarkable is that eternal inflation wasn't invented to create a multiverse. It emerged from trying to understand the early universe, and the multiverse came along for the ride. The theory wasn't designed to answer philosophical questions about reality. It was designed to solve specific technical problems in cosmology. The fact that it generates infinite bubble universes is a consequence, not a premise. Whether you find this compelling or disturbing probably says something about your philosophical temperament. But either way, you have to admit it's one heck of a ride. Our universe might be a bubble in an infinite foam, one of countless siblings we'll never meet, floating in an eternally inflating ocean that has no beginning and no end. Not bad for a theory that started as an attempt to explain why the cosmic microwave background is so boring. If eternal inflation gives us a multiverse of bubble universes, quantum mechanics gives us something arguably even stranger. A multiverse of branching realities, where every possible outcome of every quantum event actually occurs. This is the many worlds interpretation. The idea that the universe splits every time a quantum measurement happens, creating parallel branches where each possible result becomes real. It sounds like science fiction. It sounds impossible. And yet, a growing number of physicists consider it the most elegant and logically consistent way to understand quantum mechanics. Welcome to the quantum multiverse, where you're not making choices, you're splitting into versions of yourself that make every choice simultaneously. Let's start with the weirdness at the heart of quantum mechanics: superposition. In the quantum world, particles don't have definite properties until they're measured. An electron doesn't have a specific position. It exists in a superposition of all possible positions, described by a mathematical object called the wave function. When you measure the electron's position, the wave function collapses, and you find the electron at one specific location. But before the measurement, it wasn't secretly at that location all along. It genuinely existed in multiple places simultaneously, at least mathematically. This isn't interpretation. This is what the equations say, and it's confirmed by countless experiments. Quantum mechanics is weird, and we just have to deal with it. The classic illustration of this weirdness is the double-slit experiment, which has been called the most beautiful experiment in physics. Shine a beam of particles, electrons, photons, even entire molecules, at a barrier with two slits in it, and put a detector screen behind the barrier. You'd expect each particle to go through one slit or the other and pile up in two bands behind the slits. But that's not what happens. Instead, you get an interference pattern, alternating bands of high and low intensity, as if each particle went through both slits simultaneously and interfered with itself. The particle behaves like a wave, spreading out and going through both slits at once. But if you put a detector at the slits to see which one the particle goes through, the interference pattern disappears, and you get two bands like you originally expected. The act of observation changes the outcome. The particle was in superposition, and your measurement forced it to choose. Now here's the question that has haunted physicists for nearly a century. What actually happens during measurement? The standard explanation, called the Copenhagen interpretation, basically says, don't ask. The wave function collapses when you measure, and that's that. It's a practical approach that lets you calculate results without worrying too much about what's really happening. But it's philosophically unsatisfying. What counts as a measurement? Does the particle know it's being observed? Does consciousness play a role? The Copenhagen interpretation doesn't answer these questions. It just tells you to stop asking and focus on the math. The many worlds interpretation offers a radically different answer. The wave function never collapses. When you perform a measurement, you don't force the particle to choose one outcome. Instead, the universe splits, and each possible outcome occurs in a separate branch. You, the observer, also split. One version of you sees the particle go through the left slit. Another version sees it go through the right slit. Both versions are equally real, equally conscious, equally convinced they're the real you. There's no collapse, no special role for measurement or consciousness, just the relentless branching of reality into every possible configuration allowed by quantum mechanics. The famous thought experiment illustrating this is the paradox of the quantum cat, proposed by physicist Erwin Schrödinger in 1935. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. Quantum mechanics says that until the box is opened and the atom is observed, it exists in a superposition of decayed and not decayed. This means the cat is in a superposition of alive and dead. The Copenhagen interpretation says the cat is somehow both until you look, at which point it becomes one or the other. This is deeply counterintuitive. Surely the cat knows whether it's alive. Many worlds says both outcomes happen. When you open the box, the universe branches, and there's a version of you with a living cat and a version with a dead cat. The cat was never in a weird, half-alive state. You just couldn't know which branch you'd end up in until the split happened. What makes many worlds appealing to physicists is its mathematical elegance. It takes the equations of quantum mechanics at face value without adding any extra rules about collapse or measurement. The wave function just evolves according to the Schrödinger equation, smoothly and deterministically, forever. The appearance of randomness comes from the branching. Before a measurement, you don't know which branch you'll end up in, so the outcome seems probabilistic. But from a God's eye view, everything is determined. Every branch exists, and every outcome happens. It's deterministic at the level of the multiverse, even though it looks random from inside any single branch. This elegance comes with a cost, though, an enormous ontological commitment. Many worlds says that every quantum event that has ever occurred, every spin measurement, every photon absorption, every chemical reaction in your body, has split the universe into countless branches. The number of parallel realities is staggering, far more than the number of atoms in the observable universe, more than any number you could write down or even conceive. And new branches are being created constantly, at an incomprehensible rate, everywhere in the universe. It's multiverse generation on steroids. Eternal inflation gives you infinite bubble universes. Many worlds gives you infinite branching timelines within each bubble. Stack them together, and you get infinities upon infinities, a cosmic library containing not just every book that could be written, but every moment of every possible life that could be lived. Some physicists embrace this. They argue that the mathematical simplicity of many worlds outweighs the extravagance of its ontology. Better to have a clean theory with many entities than a messy theory with few. Others find the proliferation of realities absurd, an example of taking mathematical formalism too seriously. Surely, they argue, there must be a simpler explanation that doesn't require infinite parallel U's making infinite parallel choices at every moment. The debate is far from settled. Polls of physicists show many worlds gaining popularity, especially among quantum cosmologists and those working on quantum computing, but it's not the dominant view. It's one interpretation among several, each with its own strengths and weaknesses. What makes many worlds particularly mind-bending is its implications for personal identity and choice. If every decision you make is also made differently by another version of you, what does free will mean? You didn't choose to watch this video. You split into a version who watched it and a version who didn't. You're not making decisions. You're navigating a branching tree where every path is taken by some version of you. Some people find this liberating. You never really fail because some version of you succeeds at everything. Others find it paralyzing. Your choices don't matter because all choices are made anyway. And still others argue that the branching is so fundamental that our usual concepts of identity and choice just don't apply at the quantum level. Interestingly, many worlds also has potential implications for quantum computing and the philosophy of probability. If every branch is equally real, what does it mean to say that one outcome is more probable than another? The standard answer involves a concept called branch counting, or self-locating uncertainty. You don't know which branch you're on, so probability describes your ignorance rather than any objective randomness. This gets into deep philosophical waters that physicists and philosophers are still navigating. For now, many worlds remains one of the most fascinating and controversial ideas in physics. It takes the strangeness of quantum mechanics seriously and offers a logically consistent explanation at the cost of an almost unimaginable multiplication of reality. Whether the universe actually works this way, or whether some future theory will give us a cleaner picture, remains to be seen. But every time you make a measurement, every time a particle interacts with another particle, remember that according to many worlds, reality is branching. Another version of you is reading these words in a world where things went differently, and they're just as convinced they're the real you as you are. Sweet dreams. So far, we've explored multiverses created by infinite space, bubble universes from eternal inflation, and branching realities from quantum mechanics. But now we're going to tackle something that might be even more mind-bending: the possibility that the universe has more dimensions than we can perceive. Not metaphorical dimensions, not spiritual dimensions, but actual physical directions of space that we literally cannot see, touch, or move through. At least not with our current technology, and probably not ever. Welcome to the world of string theory and hidden dimensions, where the answer to some of physics' deepest mysteries might be hiding in directions we didn't even know existed. Let's start with a basic question. How many dimensions does space have? If you asked most people, they'd say 3. Up, down, left, right, forward, backward. Add time as a 4th dimension, and you've got the 4-dimensional space-time of Einstein's relativity. This seems obviously correct. After all, we experience 3 spatial dimensions every day. We can point in 3 perpendicular directions, and that's it. There's no 4th spatial direction to point to. Case closed, right? Well, not so fast. Because theoretical physics has been telling us for decades that 3 dimensions might not be the whole story. In fact, if string theory is correct, there could be 6 or 7 additional dimensions of space that we've somehow completely failed to notice. Which raises an obvious question. Where the heck are they? String theory emerged in the late 1960s and 1970s as physicists tried to understand the strong nuclear force that holds protons and neutrons together. The early versions had problems. They predicted particles that didn't exist and required 26 dimensions of spacetime to work mathematically. 26 dimensions. That's 22 more than we observe, which is quite a discrepancy. You'd think physicists would have given up at that point. But physicists are a stubborn bunch. They kept working on the theory, and by the 1980s, a new version called superstring theory had emerged. This version incorporated supersymmetry, a proposed relationship between different types of particles, and it only required 10 dimensions. Only. as if requiring 6 extra dimensions instead of 22 was a modest improvement. But in the world of theoretical physics, reducing your extra dimensions by 16 counts as progress. Later developments unified the various versions of string theory into something called M-theory, which requires 11 dimensions, 10 of space and 1 of time. The M supposedly stands for membrane, master, mother, or mystery, depending on who you ask. The physicist Edward Witten, who proposed M-theory in 1995, has said he originally meant it to stand for magic or mystery, but is now inclined to think of it as standing for membrane. Whatever the name means, the implication is the same. If this theory is correct, there are 7 spatial dimensions beyond the 3 we experience. 7 invisible directions that particles might be vibrating in, forces might be propagating through, and entire universes might be hiding within. It's like discovering that your house has 7 extra rooms you never knew about. Except these rooms exist in directions you can't point to, and might contain alien physics. So where are these extra dimensions? Why can't we see them? The most common answer is called compactification. The idea is that the extra dimensions aren't stretched out like the 3 big dimensions we experience. They're curled up, wrapped around themselves at scales so tiny that we can't detect them. Imagine an ant walking on a garden hose. From far away, the hose looks like a one-dimensional line, but up close, the ant can walk along the length of the hose or around its circumference. There are 2 dimensions, but one of them is curled up so small that it's invisible from a distance. String theory suggests something similar. The extra dimensions are curled up at the Planck scale, about 10 to the minus 35 meters. That's 100 billion times smaller than a proton. No experiment we can currently build, or probably ever build, can probe distances that small directly. The extra dimensions are hidden not by magic, but by geometry. But how exactly are these dimensions curled up? This is where things get mathematically intense and geometrically beautiful. The extra 6 dimensions in superstring theory are thought to be compactified into structures called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. These are 6-dimensional shapes with very specific mathematical properties. They're compact, they have a certain type of curvature, and they preserve some of the supersymmetry that string theory requires. If you've ever seen visualizations of Calabi-Yau manifolds, they look like intricate, folded, crystalline structures with holes and curves and surfaces wrapping around each other in ways that defy intuition. They're gorgeous, in a deeply abstract mathematical sense. They're also impossible to visualize accurately because our brains evolved to handle 3 dimensions, not 6. Any picture you see of a Calabi-Yau manifold is a projection, a shadow of the true shape, like trying to understand a cube by looking at its 2-dimensional shadow on a wall. The specific shape of the Calabi-Yau manifold matters enormously because it determines the physics we observe in the 3 large dimensions. Different shapes lead to different numbers of particle families, different force strengths, different everything. This is both exciting and problematic. It's exciting because it means string theory might explain why our universe has the specific particles and forces it does. They emerge from the geometry of the hidden dimensions. But it's problematic because there are an astronomical number of possible Calabi-Yau shapes. Remember the string theory landscape we mentioned earlier? Those 10 to the power of 500 possible configurations? Many of those come from different ways of compactifying the extra dimensions. Each shape gives a different universe. Our universe corresponds to one particular shape, but string theory doesn't tell us which one. It's like being handed a menu with 10 to the 500 options and being told your dinner is definitely on there somewhere. Good luck finding it before the restaurant closes, in this case before the heat death of the universe. Now, compactification isn't the only way to hide extra dimensions. M-theory introduces another possibility: brains. A brain, short for membrane, is a higher dimensional object that exists in the full higher dimensional space of M-theory. Our entire observable universe might be a 3-dimensional brain floating in a higher dimensional bulk. Imagine a sheet of paper floating in a room. The paper is 2-dimensional. The room is 3-dimensional. Creatures living on the paper would only experience 2 dimensions, even though they're surrounded by a 3rd dimension they can't access. Similarly, we might be stuck on a 3-dimensional brain, unable to perceive the higher dimensional bulk around us. Other brains could be floating nearby, parallel to ours, containing their own universes with their own physics. These parallel brain worlds would be separated from us not by distance in the 3 dimensions we know, but by distance in a dimension we can't perceive, maybe just a millimeter away in a direction we can't point to. This brain world scenario has some fascinating implications. One of the biggest mysteries in physics is the weakness of gravity. Compared to the other fundamental forces, gravity is pathetically weak. The electromagnetic force between two electrons is about 10 to the power of 42 times stronger than the gravitational force between them. That's a 1 with 42 zeros after it. Why is gravity so feeble? One possibility is that gravity is actually just as strong as the other forces, but it's being diluted because it spreads into the extra dimensions. In brain world models, the particles that make up ordinary matter, electrons, quarks, photons, are confined to our brain. They can't move into the bulk. But gravitons, the hypothetical particles that transmit gravity, might be able to escape into the higher dimensional space. Gravity would then appear weak to us because most of its strength is leaking away into dimensions we can't detect. It's like hearing music from a party in another building. The sound is weak not because the music is quiet, but because most of it is going in directions you're not facing. This idea has testable consequences. If gravity leaks into extra dimensions, then at very short distances, shorter than the size of the extra dimensions, gravity should behave differently than Newton and Einstein predicted. Experiments have searched for deviations from standard gravity at sub-millimeter scales, looking for evidence of extra dimensions. So far, nothing definitive has been found, which puts constraints on how big the extra dimensions can be. They have to be smaller than about 40 micrometers, roughly the width of a human hair. That's still much larger than the Planck scale, so there's a window where extra dimensions could exist without us having detected them yet. Future experiments, including some at particle colliders, might probe these scales more precisely and either find evidence for extra dimensions or rule out more possibilities. Speaking of particle colliders, one of the more exotic predictions of extra-dimensional theories is the possible production of microscopic black holes. In standard physics, creating a black hole requires compressing matter to incredible densities, far beyond anything we could achieve in a laboratory. But if gravity becomes stronger at short distances due to extra dimensions, the energy threshold for black hole creation drops dramatically. At the energies achieved by the Large Hadron Collider, it might be possible to create tiny black holes that would immediately evaporate through Hawking radiation. These wouldn't be dangerous. They'd be too small and too short-lived to swallow anything. But their signatures in particle detectors would be unmistakable evidence for extra dimensions. Physicists have searched for these signatures and haven't found them, which again puts constraints on the theories. But the search continues because the discovery would be revolutionary. The extra dimensions of string theory also connect to the multiverse in a deep way. We've already discussed how different compactifications of the extra dimensions give different physics, leading to a landscape of possible universes. But brain world scenarios add another layer. If multiple brains exist in the bulk, each could host its own universe with its own inhabitants. These parallel brain worlds would be physically real, existing in the same higher dimensional space as us, but forever inaccessible. Unless, that is, brains can collide. Some cosmological models propose that the Big Bang itself was caused by two brains colliding in the bulk. The energy of the collision would have ignited the hot, dense conditions that started our universe. If this ekpyrotic scenario is correct, our universe might be the result of an interdimensional fender bender, and similar collisions might be happening elsewhere in the bulk, creating new universes all the time. It's worth stepping back and acknowledging how speculative all of this is. String theory and its extra dimensions remain unproven. We have no direct experimental evidence that strings exist, that extra dimensions are real, or that our universe is a brain. The mathematics is beautiful and the ideas are compelling, but beauty and compellingness aren't the same as truth. Many physicists are skeptical, arguing that string theory has failed to make testable predictions after decades of development. Others remain hopeful that future experiments or observations will provide the evidence needed to confirm or refute these ideas. The debate is ongoing, and it touches on deep questions about what science is and what counts as a scientific theory. But even if string theory turns out to be wrong, the exploration of extra dimensions has enriched physics and mathematics in profound ways. New mathematical tools have been developed. New connections between different areas of physics have been discovered, and our conception of what reality could be has expanded dramatically. A century ago, suggesting that space might have more than 3 dimensions would have seemed absurd. Today, it's a mainstream research program pursued by thousands of physicists around the world. Even if the extra dimensions are never found, the search itself has pushed the boundaries of human knowledge. So the next time you stub your toe on a table and curse the 3-dimensional solidity of the world, remember, There might be 7 more directions you're not aware of. The universe might be far stranger and more spacious than it appears. And somewhere, in a dimension you can't point to, there might be an entire parallel universe just a millimeter away, forever beyond your reach. Physics has come a long way from assuming that what you see is all there is. Now we're pretty sure that what you see is barely a fraction of what exists. Whether that's exciting or terrifying probably depends on whether you find comfort or claustrophobia in the familiar 3 dimensions we call home. We've spent the last several chapters exploring the theoretical landscape of the multiverse. Infinite spaces, bubble universes, quantum branching, hidden dimensions. It's all fascinating, but at some point, a reasonable person might ask, is any of this actually testable? Can we move beyond elegant mathematics and philosophical speculation to something that could be confirmed or ruled out by experiment? The answer is a qualified yes, and one of our best hopes for finding evidence lies beneath the Swiss-French border, in a 27-kilometer circular tunnel housing the most complex machine humanity has ever built, the Large Hadron Collider. Welcome to CERN, where physicists are literally smashing particles together at nearly the speed of light, hoping the debris will reveal secrets about extra dimensions, supersymmetry, and maybe, just maybe, the multiverse itself. The Large Hadron Collider, or LHC, is operated by CERN, the European Organization for Nuclear Research, which is one of those names that sounds much more impressive in French. Located near Geneva, straddling the border between Switzerland and France, the LHC is the largest and most powerful particle accelerator ever constructed. It accelerates protons to 99.9999991% of the speed of light, and then smashes them together head-on, releasing enough energy in a tiny volume to recreate conditions that existed a trillionth of a second after the Big Bang. If you want to understand the fundamental nature of reality, you need to look at reality's smallest pieces. And to see those pieces, you need to hit them really, really hard. The LHC is basically a $10 billion hammer designed to break open the universe's tiniest piñatas. The numbers involved in the LHC are genuinely staggering. The main ring is 27 kilometers in circumference, buried about 100 meters underground. It contains 9,593 superconducting magnets cooled to minus 271 degrees Celsius, colder than outer space, to bend and focus the particle beams. Each beam contains about 3,000 bunches of protons, with roughly 100 billion protons per bunch. These beams circulate in opposite directions, completing 11,000 laps per second before being steered into collision at 4 points around the ring. At each collision point sits a massive detector, ATLAS, CMS, ALICE, and LHCb, designed to capture and analyze the spray of particles produced when protons annihilate each other. ATLAS alone weighs 7,000 tons and contains more iron than the Eiffel Tower. Building and operating this machine required collaboration among over 10,000 scientists from more than 100 countries. It's one of the most ambitious scientific projects in human history, and it exists primarily to answer questions about the fundamental structure of matter and space. The LHC's most famous achievement so far is the discovery of the Higgs boson in 2012, which confirmed the existence of the Higgs field, the mechanism that gives particles their mass. This was a triumph for the standard model of particle physics, the theory that describes all known fundamental particles and 3 of the 4 fundamental forces. But the standard model, despite its successes, is incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't tell us why the universe is made of matter rather than antimatter. And it has some troubling features that look like fine-tuning, parameters that seem unnaturally precise, as if someone carefully adjusted the cosmic dials to make the universe work. Physicists hate fine-tuning. It makes them suspicious that they're missing something deeper. And that's where the search for physics beyond the standard model comes in. One of the leading candidates for beyond standard model physics is supersymmetry, often abbreviated as SUSY. Supersymmetry proposes that every known particle has a heavier superpartner, a kind of shadow twin with different quantum properties. Electrons would have selectrons, quarks would have squarks, photons would have photinos. Yes, the naming convention is exactly as silly as it sounds. Physicists apparently couldn't resist adding S to the front of everything. But silly names aside, supersymmetry would solve several problems in particle physics. It would help explain the Higgs boson's mass, provide a natural candidate for dark matter, and, crucially for our story, it's a key ingredient in string theory. If supersymmetric particles exist, It would be strong, indirect evidence that string theory is on the right track, which would in turn support the extra dimensions and multiverse scenarios we've been discussing. The LHC has been searching for supersymmetric particles since it started operating. The idea is straightforward. If superpartners exist and are heavy enough to produce at LHC energies, they should appear in the collision debris. Detectors would see unusual patterns, events with lots of missing energy, or unusual combinations of particles that don't fit the standard model. Unfortunately, despite years of searching and analyzing petabytes of data, no supersymmetric particles have been found. This doesn't definitively rule out supersymmetry. The superpartners might be heavier than the LHC can produce, or they might decay in ways that are hard to detect. But the failure to find them has been disappointing for many theorists who expected Susie to show up by now. Some versions of supersymmetry have been ruled out entirely. Others have been pushed into increasingly narrow corners of parameter space, requiring more and more fine-tuning to remain viable, which somewhat defeats the purpose of proposing supersymmetry in the first place. But supersymmetry isn't the only game in town. The LHC is also searching for direct evidence of extra dimensions through several different approaches. One approach involves looking for missing energy in collision events. Remember, if extra dimensions exist and gravity can leak into them, then some of the energy from a collision might disappear into those hidden dimensions. Detectors at the LHC meticulously track all the particles produced in each collision and add up their energies and momenta. If the totals don't balance, if energy seems to vanish without a trace, it could indicate that something escaped into a dimension we can't observe. So far, no such anomalous missing energy has been conclusively detected, but the search continues with increasingly precise measurements. Another approach is the search for microscopic black holes. In standard physics, creating a black hole requires compressing matter to densities far beyond anything achievable in a laboratory. But if extra dimensions exist and gravity becomes stronger at short distances, the energy threshold for black hole formation drops dramatically. At LHC energies, it might be possible, in some theoretical scenarios, to briefly create tiny black holes in proton collisions. These wouldn't be dangerous. They would be subatomic in size and would evaporate almost instantly through a process called Hawking radiation, named after physicist Stephen Hawking. The evaporation would produce a distinctive spray of particles that detectors could identify. Finding such a signature would be spectacular evidence for extra dimensions. Not finding it tells us that either extra dimensions don't exist, or they're smaller than certain models predict, or the energy threshold is higher than the LHC can reach. Before the LHC started operating, there was actually a minor public panic about the possibility of creating dangerous black holes that could swallow the Earth. Lawsuits were filed. Physicists had to patiently explain that cosmic rays, particles from space that bombard Earth constantly, have energies far exceeding what the LHC produces, and they've been hitting planets, moons, and stars for billions of years without creating any. Earth-eating black holes. If it were possible to destroy a planet this way, there would be no planets left to worry about. The panic subsided, the LHC turned on, and unsurprisingly, we're all still here. Though I suppose if we had been swallowed by a black hole, we wouldn't be around to notice, which is a comforting thought if you think about it for exactly 0 seconds. The LHC also searches for other exotic phenomena that could hint at multiverse physics. Gravitons, the hypothetical particles that carry the gravitational force, might be produced in collisions and either escape into extra dimensions or resonate in ways that reveal the geometry of hidden space. Heavy particles predicted by various beyond standard model theories could show up, providing clues about the underlying structure of reality. Even subtle deviations from standard model predictions could hint at new physics lurking just beyond our current understanding. The LHC is essentially a fishing expedition in the unknown, casting an extremely expensive net into the quantum sea and hoping to catch something unexpected. Now, it's important to be honest about the limitations here. The LHC, despite being the most powerful particle accelerator ever built, operates at energies that are still far below the scales where most multiverse theories make definitive predictions. The Planck scale, where quantum gravity effects become important and where extra dimensions might directly reveal themselves, is about a quadrillion times higher than LHC energies. We can't build an accelerator that powerful. It would need to be galaxy-sized, which presents certain practical difficulties. So the LHC is looking for indirect signatures, low-hanging fruit, hints and clues rather than definitive proof. It's possible that the multiverse is real, but that no evidence will ever appear at the energies we can achieve. That would be frustrating, but it's the reality of doing experimental physics at the frontier. Despite these limitations, the LHC has already taught us valuable lessons. The discovery of the Higgs boson confirmed a key piece of the Standard Model and opened new avenues for investigation. The non-discovery of supersymmetry at expected energies has forced theorists to rethink their models, which is how science progresses. The constraints on extra dimensions and microscopic black holes have narrowed the space of viable theories. Even null results are results. They tell us where not to look and which ideas need revision. The LHC is currently undergoing upgrades to increase its luminosity, the rate at which collisions occur, which will allow physicists to accumulate more data and potentially see rare processes that have been statistically invisible so far. The high-luminosity LHC, scheduled to operate starting in the late 2020s, will produce 10 times more collisions than the current machine, dramatically improving the chances of discovering subtle new physics. There's also ongoing discussion about even more powerful future colliders. The proposed Future Circular Collider at CERN would be 100 kilometers in circumference and would reach energies several times higher than the current LHC. China is planning its own next-generation collider. These machines, if built, would probe deeper into the unknown and might finally reveal whether our theoretical speculations about extra dimensions and the multiverse have any connection to reality. What would it take to confirm the multiverse using particle physics? Honestly, a single smoking gun discovery is unlikely. More plausibly, we would accumulate a pattern of evidence, discovery of supersymmetric particles consistent with string theory, detection of signatures suggesting extra dimensions, observation of phenomena that only make sense in a multiverse. Framework. Each piece individually might have alternative explanations, but together they could build a compelling case. Science often works this way, not through single dramatic revelations, but through the gradual accumulation of converging evidence. The multiverse might never be proven in the way a mathematical theorem is proven, but it could become the best explanation for a wide range of observations. For now, the LHC continues its work, collision by collision, event by event, searching for cracks in the Standard Model that might let us glimpse what lies beyond. Thousands of physicists analyze the data, develop new search strategies, and refine their theoretical predictions. It's painstaking work, often unglamorous, rarely producing headlines. But somewhere in those petabytes of collision data, there might be a signal, a hint that the universe is stranger than we thought, that extra dimensions are real, that we live in just one pocket of an infinite multiverse. The hunt continues, and the hunters are patient. After all, they've built a machine that can recreate the conditions of the early universe. They can wait a few more years for nature to reveal its secrets. There's something almost poetic about the whole endeavor. Humans, creatures who evolved to hunt animals on an African savanna, have built a machine that probes the structure of space-time itself. We've taken the curiosity that once helped us find food and shelter and directed it toward understanding the fundamental nature of existence. The LHC is, in a very real sense, a monument to human ambition, a physical manifestation of our refusal to accept that some questions are unanswerable. Whether it ultimately reveals evidence of the multiverse or tells us we're barking up the wrong theoretical tree, it represents something profound about what our species is capable of when we work together toward a common goal. Not bad for a bunch of hairless apes who figured out how to ask really, really big questions. We've talked about the Large Hadron Collider hunting for evidence of extra dimensions and supersymmetry. We've explored eternal inflation spawning bubble universes and quantum mechanics splitting reality into branching timelines. But now we need to confront one of the most controversial and philosophically loaded ideas in all of modern physics: the string theory landscape. This is the concept that there might be 10 to the power of 500 different possible universes, each with its own physical laws, its own constants of nature, its own version of reality. And our universe, with its seemingly miraculous fine-tuning for life, might just be one random draw from this incomprehensibly vast cosmic lottery. Get ready, because we're about to wrestle with some of the deepest questions about why the universe is the way it is, and whether why is even the right question to ask. Let's start with a puzzle that has haunted physicists for decades: the fine-tuning problem. Our universe appears to be set up with remarkable precision to allow for the existence of complex structures: stars, planets, chemistry, life. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the cosmological constant, seem to be dialed in to exactly the right values. Change them even slightly, and the universe becomes sterile. Make gravity a bit stronger, and stars burn out too quickly for life to evolve. Make it weaker, and matter never clumps together to form stars at all. Tweak the strong nuclear force, and atomic nuclei either fall apart or fuse too easily, making complex chemistry impossible. Adjust the cosmological constant, the energy density of empty space, and the universe either expands so fast that galaxies never form, or collapses back on itself before anything interesting happens. The numbers are genuinely striking. The cosmological constant, for instance, is about 10 to the minus 122 in natural units. That's a decimal point followed by 121 zeros and then a 1. If it were just a tiny bit larger, even by a factor of 100 or so, the universe would have blown apart before galaxies could form. If it were negative and too large, the universe would have collapsed. We exist in an incredibly narrow window of possibility, balanced on a cosmic knife's edge. And this isn't the only example. The ratio of electromagnetic to gravitational force strength, the mass difference between protons and neutrons, the number of spatial dimensions, all of these seem fine-tuned for a universe capable of supporting observers. It's as if someone very carefully adjusted 100 different dials to exactly the right settings, then stepped back and let the universe run. This apparent fine-tuning has led some people to conclude that the universe was designed, that an intelligent creator deliberately set the constants to allow for life. This is the argument from design, updated for the age of particle physics. But most scientists are uncomfortable with this conclusion, not because they have anything against religion, but because a designer did it isn't a scientific explanation. It doesn't make predictions. It doesn't tell you what to look for next. It's a conversation stopper rather than a conversation starter. Physicists want to understand why the constants have the values they do, not throw up their hands and invoke mystery. Enter the string theory landscape. As we discussed earlier, string theory requires extra dimensions, and those extra dimensions can be compactified in an enormous number of different ways. Each compactification, each different shape for the hidden dimensions, gives rise to a different set of physical laws, different particle masses, different force strengths. The number of possible compactifications is estimated at around 10 to the power of 500. That's not a number anyone can visualize. It's not even a number you can meaningfully compare to other large numbers. There are roughly 10 to the 80 atoms in the observable universe. 10 to the 500 is so much larger that 10 to the 80 might as well be 0 by comparison. We're talking about a space of possibilities so vast that every conceivable set of physical laws exists somewhere within it. Now here's where it gets philosophically interesting. If eternal inflation is true, and if string theory is correct, then each of these 10 to the 500 possible configurations might actually be realized in some bubble universe somewhere. The multiverse would contain universes with every possible set of laws, universes where gravity is stronger or weaker, where there are more or fewer particle types, where the cosmological constant takes every possible value. Most of these universes would be hostile to life. Stars wouldn't form, or atoms wouldn't be stable, or the universe would be too short-lived for anything interesting to happen. But a tiny fraction, a vanishingly small subset, would have conditions compatible with observers. And naturally, observers can only observe universes they can exist in. This is the anthropic principle, and it's either a profound insight or a trivial tautology, depending on who you ask. In its weak form, it simply says that we must find ourselves in a universe compatible with our existence. This is obviously true and not very controversial. Of course, we don't live in a universe where chemistry is impossible. If we did, we wouldn't be here to notice. But in its stronger forms, the anthropic principle becomes a tool for explaining fine-tuning without invoking design. If there are 10 to the 500 possible universes, and observers can only exist in the rare ones with life-friendly parameters, then it's no surprise that we find ourselves in such a universe. We're not special, we're just in one of the lucky bubbles. Selection bias explains what looks like cosmic purpose. Think of it this way. Imagine you wake up in a hotel room that happens to have exactly the right temperature, the right air pressure, the right amenities for your comfort. You might be tempted to think the hotel was designed specifically for you. But then you learn that the hotel has 10 to the 500 rooms, each with randomly different conditions, and that you were placed in whichever room you could survive in. Suddenly, the apparent design dissolves. You're not special, you're just in a room you can exist in, and you never had the chance to experience the rooms filled with toxic gas or extreme temperatures. The fine-tuning of your room isn't evidence of design, it's evidence of selection. The anthropic principle combined with the string landscape offers a naturalistic explanation for fine-tuning that doesn't require a designer. The universe isn't fine-tuned for us. We're adapted to the universe we happen to find ourselves in, and we could only find ourselves in one of the rare universes that permits our existence. It's a complete inversion of the design argument. Instead of the universe being made for us, we exist because we're in a universe that happens to allow existence. Randomness plus selection equals apparent purpose. Not everyone is happy with this explanation. Critics argue that it's untestable and unscientific. If every possible universe exists somewhere, then the theory predicts nothing specific about our universe. Anything we observe is compatible with, you're in one of the universes where that happens. This feels like cheating to many physicists. A theory that can't be wrong isn't really a theory at all. The philosopher Karl Popper argued that scientific theories must be falsifiable. They must make predictions that could, in principle, be proven wrong. If the landscape predicts everything, it predicts nothing, and it fails Popper's criterion. Defenders of the landscape respond that the situation is more nuanced. The landscape doesn't predict that anything goes. It predicts a statistical distribution of universes. Most universes have a large cosmological constant. Only rare ones have a small one. If we observe a small cosmological constant, which we do, that's consistent with being in one of the rare, habitable universes. Moreover, the landscape makes some specific predictions. The cosmological constant should be small but not zero, which matches observation. The particle physics should fall within certain ranges. These predictions can, in principle, be tested. The landscape isn't quite as unfalsifiable as critics claim, though the debate continues. There's also a deeper philosophical objection. The anthropic explanation feels unsatisfying to many people because it seems to give up on finding a fundamental reason for the constants. Traditional physics hopes to derive the constants from first principles, to show that they couldn't have been otherwise, that some deep mathematical structure dictates their values. The landscape says, nope, the constants are environmental, random, chosen by cosmic lottery. There's no deeper explanation. The buck stops at, that's just how it is in our bubble. For physicists who believe in the ultimate comprehensibility of nature, this feels like defeat. But maybe our expectations are the problem. For centuries, humans assumed there was something special about Earth. It was the center of the universe, the stage on which cosmic drama played out. Copernicus and his successors showed us that Earth is just one planet among many, orbiting one star among billions, in one galaxy among trillions. There's nothing cosmically special about our location. The anthropic landscape extends this humility to the laws of physics themselves. Maybe our laws of physics aren't special either. Maybe they're just one possibility among an unimaginable number, and we happen to live in this one because we couldn't live in most others. It's cosmic modesty taken to its logical extreme. The landscape also raises fascinating questions about what laws of physics even mean. We usually think of physical laws as universal, absolute, the same everywhere and every when. But if the landscape is real, then what we call laws are actually more like local conditions, features of our particular bubble that don't hold in other bubbles. The laws of physics would be no more fundamental than the fact that water is wet on Earth. They'd be contingent facts about our environment, not eternal truths about reality. This is a radical reconceptualization of what physics is and what it can hope to explain. Some physicists find the landscape beautiful in its own way. It offers a complete theory of everything, literally everything, including all possible everythings. It explains fine-tuning without supernatural intervention. It connects deep ideas in string theory, cosmology, and quantum mechanics into a unified framework. And it makes a strange kind of sense. If the multiverse contains all possibilities, then of course some possibilities include observers, and of course those observers wonder why their universe seems designed. The mystery dissolves once you realize you're only seeing a biased sample. Others find it depressing. They became physicists to find ultimate explanations, to understand why the universe is the way it is. The landscape says there is no why, or rather, the why is just statistics and selection. The universe isn't designed, it isn't necessary, it isn't even unique. It's just one random outcome among infinitely many, no more special than a particular shuffle of a deck of cards. For scientists who dreamed of uncovering the mind of God, as Einstein put it, the landscape offers a decidedly less romantic picture. Not the mind of God, just the randomness of everything. Whether the string landscape is true remains an open question. String theory itself is unproven, and the landscape emerges from the most speculative parts of that unproven theory. Many physicists doubt we'll ever know for certain whether other universes with different laws exist. But the landscape represents something important regardless of its truth. It's a coherent alternative to design-based explanations for fine-tuning. It shows that you don't need a creator to explain why the universe permits life. Randomness, selection, and vast numbers can do the job. Whether you find that liberating or deflating probably says something about your philosophical temperament. But either way, you have to admit, it's one heck of a cosmic vision. 10 to the 500 universes, each with its own laws, floating in an eternal multiverse, most of them barren and cold, a few of them teeming with observers wondering why they got so lucky. Welcome to the landscape. Population, everything that's possible. And if that thought keeps you up at night, just remember, somewhere in the landscape there's a version of you who finds it deeply comforting. Whether that makes you feel better or worse is entirely up to you, and also, statistically speaking, up to every other version of you scattered across the infinite possibilities of existence. We've spent a lot of time exploring the various flavors of multiverse theory: infinite space, eternal inflation, quantum branching, extra dimensions, the string landscape. It's all genuinely fascinating stuff, and some very smart people take it seriously. But here's the thing, not everyone is on board. In fact, some of the most respected physicists in the world think the multiverse is, to put it bluntly, nonsense. Not just unproven, but unprovable. Not just speculative, but fundamentally unscientific. Before we go any further down the multiverse rabbit hole, we need to hear from the skeptics. Because if they're right, we might have been exploring an elaborate fantasy dressed up in mathematical language. And if they're wrong, understanding their objections will only make the case for the multiverse stronger. The central criticism of multiverse theories comes down to one word: falsifiability. This concept was championed by the philosopher Karl Popper in the 20th century, and it's become a cornerstone of how scientists distinguish science from non-science. The idea is simple. A scientific theory must make predictions that could, in principle, be proven wrong. If there's no possible observation or experiment that could refute a theory, then the theory isn't scientific. It's something else, maybe philosophy, maybe theology, maybe wishful thinking, but not science. Evolution is scientific because we could find fossils in the wrong geological strata that would disprove it. General relativity is scientific because we could observe light bending the wrong way around massive objects. These theories stuck their necks out and invited the universe to prove them wrong. So far, the universe hasn't taken them up on it, which is why we consider them well supported. The multiverse, critics argue, fails this test spectacularly. By definition, other universes in the multiverse are causally disconnected from ours. We can't see them, travel to them, or receive any signals from them. If the many worlds interpretation is correct, the other branches of quantum reality split off completely and forever. If eternal inflation is true, the other bubble universes are beyond our cosmic horizon, unreachable even in principle. If the string landscape contains 10 to the 500 possible configurations, we have no way of checking which ones actually exist. The multiverse makes no predictions about what we'll observe in our universe that couldn't also be explained by other theories. It's unfalsifiable by design, and that, critics say, means it isn't science. Physicist Paul Steinhardt, one of the original architects of inflationary cosmology, has become one of its harshest critics. He argues that eternal inflation, which naturally leads to the multiverse, is actually a sign that inflation theory has gone off the rails. The original appeal of inflation was that it explained specific features of our universe: its flatness, its uniformity, the particular patterns in the cosmic microwave background. But eternal inflation says that anything that can happen does happen somewhere in the multiverse. This explanatory power is an illusion, Steinhardt argues. If every possible outcome occurs, then inflation predicts everything, and therefore predicts nothing. It's like a fortune teller who covers all bases. No matter what happens, they can claim they were right. Cosmologist George Ellis has made similar arguments, warning that multiverse thinking threatens to undermine the empirical foundations of physics. If we accept theories that can't be tested, we open the door to all sorts of speculation that has no connection to reality. What separates physics from mythology, Ellis asks, if not the requirement that our theories face experimental judgment? He doesn't deny that the multiverse is mathematically possible or even aesthetically appealing. He just doesn't think it qualifies as science. And in a world where science carries enormous cultural authority, calling something scientific when it isn't is a kind of intellectual fraud. The debate got particularly heated in 2014 when physicists George Ellis and Joseph Silk published an article in Nature titled "Scientific Method: Defend the Integrity of Physics." They argued that some theoretical physicists had abandoned the traditional requirement of experimental verification, replacing it with criteria like mathematical elegance and explanatory power. This, they warned, was a dangerous path that could lead physics away from its empirical roots. The article sparked a fierce response from multiverse proponents, who accused Ellis and Silk of being old-fashioned and failing to appreciate how physics at the frontier necessarily differs from physics in textbooks. Defenders of the multiverse have several responses to these criticisms. First, they point out that falsifiability isn't the only criterion for scientific theories. Philosophers of science have long recognized that the relationship between theory and evidence is more complex than Popper suggested. Theories are supported not just by direct tests, but by their coherence with other established theories, their explanatory scope, and their ability to make sense of otherwise puzzling observations. The multiverse emerges naturally from well-tested theories like inflation and quantum mechanics. It's not an arbitrary add-on, but a logical consequence. If you accept the parent theories, the multiverse comes along for the ride. Second, the multiverse does make some predictions, even if they're statistical rather than specific. If the string landscape is correct, and we're selected for by anthropic reasoning, we should expect to find ourselves in a universe that's just barely compatible with life, not fine-tuned to perfection, but hovering near the boundaries of habitability. Some physicists argue this matches what we observe. The cosmological constant, for instance, is small enough to allow galaxy formation, but not much smaller. Exactly what you'd expect if it were selected from a random distribution. Critics counter that this is post hoc reasoning, fitting the theory to observations rather than predicting them in advance. The argument continues. Third, some defenders argue that we should update our philosophy of science to match the realities of modern physics. When physics probes scales far beyond direct human experience, the Planck scale, the cosmic horizon, the quantum realm, traditional notions of testability may need revision. This doesn't mean abandoning empiricism, but it might mean accepting different kinds of evidence and different standards of support. Mathematics, for instance, can guide us in realms where experiments can't reach. If the math says the multiverse exists, and the math is derived from well-tested principles, maybe that counts for something even without direct observation. This last argument is the most controversial because it sounds dangerously like faith. Trust the math is fine when the math leads to predictions we can check, but what happens when it doesn't? Critics worry that physics is becoming a mathematical game detached from physical reality, that theorists are exploring what's mathematically possible rather than what's actually true. The history of physics is littered with beautiful mathematical theories that turned out to be wrong. Elegance and consistency are not guarantees of truth. So where does this leave us? The honest answer is, in genuine uncertainty. The multiverse is not proven. It may never be proven. It may be unprovable in principle. But it's also not disproven, and it emerges from our best current theories about cosmology and quantum mechanics. The scientific community is genuinely divided. Some brilliant physicists are convinced the multiverse is real. Other equally brilliant physicists think it's elaborate nonsense. This isn't a case of consensus versus crackpots. It's a legitimate scientific debate about the nature of science itself. Perhaps the most important lesson from this controversy is that science at the frontier is messy. Textbooks present science as a clean progression of hypotheses, experiments, and conclusions. Real science, especially at the cutting edge, is full of ambiguity, disagreement, and unresolved questions. The multiverse debate forces us to confront deep issues about what science is, what counts as evidence, and how we should think about realms beyond direct observation. These questions don't have easy answers, and pretending they do would be dishonest. For now, the multiverse remains a tantalizing possibility, supported by theoretical arguments, consistent with observations, but forever hovering at the edge of what we can know for certain. All right, let's get to the question that's probably been nagging at the back of your mind since we started this journey. If parallel universes exist, can we visit them? Can we hop from our reality to another one where things turned out differently? Can we meet our cosmic doubles, fix our past mistakes in an alternate timeline, or escape to a universe where pizza is a health food? The short answer is, almost certainly not. The long answer involves some of the strangest objects in theoretical physics, wormholes, and why they're much easier to imagine than to actually use. Buckle up, because we're about to explore the ultimate cosmic shortcuts. and then we're going to explain why they probably don't work. Wormholes, also known as Einstein-Rosen bridges, are theoretical structures that could connect distant points in space-time. The concept emerged in 1935 when Albert Einstein and physicist Nathan Rosen were analyzing the mathematics of black holes. They found that the equations of general relativity allowed for a kind of tunnel through space-time, a shortcut that could link two separate regions of the universe, or even two separate universes entirely. Imagine space-time as a sheet of paper. Normally, to get from one point to another, you have to travel along the surface. But if you fold the paper so 2 points touch, you could punch a hole through and take a shortcut. That's essentially what a wormhole would do, except instead of paper, it's the fabric of space and time, and instead of punching, it's, well, physics we don't fully understand. The idea captured the public imagination immediately, and it's been a staple of science fiction ever since. Want to travel to a distant galaxy without spending millions of years in transit? Take a wormhole. Want to visit a parallel universe? Find a wormhole that connects to it. Want to travel through time? Some wormhole configurations might even allow that. It's the ultimate cosmic convenience, the subway system of the universe. Unfortunately, like most things that seem too good to be true, wormholes come with some serious problems. The first problem is that we've never actually observed a wormhole. They're purely theoretical constructs that emerge from the mathematics of general relativity. Just because the equations allow something doesn't mean it exists. The equations also technically allow for closed time-like curves, naked singularities, and all sorts of other exotic phenomena that we have no evidence for. Mathematical possibility is not physical reality. Wormholes might exist somewhere in the universe, formed by extreme conditions we haven't witnessed. Or they might be mathematical curiosities with no physical counterpart, like the square root of -1, useful for calculations, but not something you can point to. The second problem is stability. Even if wormholes could form, the simplest versions, the Einstein-Rosen bridges, are incredibly unstable. They would snap shut almost instantly, far too quickly for anything to pass through. In technical terms, the throat of the wormhole would collapse before light could traverse it, let alone a spaceship or a person. It would be like trying to walk through a door that slams shut in a trillionth of a second. Good luck with that. The wormhole might connect 2 points, but that connection would last for an unmeasurably brief moment before disappearing forever. To keep a wormhole open long enough to be useful, you would need something very strange, exotic matter. This isn't the regular matter that makes up atoms and molecules. It's a hypothetical substance with negative energy density. While positive energy density causes space-time to curve in one direction, negative energy would curve it the other way, potentially propping open the throat of a wormhole and preventing it from collapsing. Physicist Kip Thorne worked out the requirements for a traversable wormhole in the 1980s, and the exotic matter requirement was central. Without it, no passage. With it, maybe, just maybe, you could take a shortcut through the cosmic fabric. Here's the problem. We don't know if exotic matter exists. Quantum field theory suggests that something like negative energy might be possible under certain conditions. The Casimir effect, for instance, involves tiny negative energy densities between closely spaced metal plates. But these effects are minuscule, nowhere near the amounts needed to prop open a wormhole large enough for a human, let alone a spacecraft. Getting enough exotic matter would require physics far beyond our current capabilities. We're talking about manipulating space-time itself, which is not something you can do with a really big budget and good intentions. Even if we could somehow create or find exotic matter, building a traversable wormhole would be an engineering challenge that makes the Large Hadron Collider look like a child's toy. You'd need to manipulate gravity on scales we can barely conceive, create structures in space-time without being crushed by the forces involved, and somehow stabilize the whole thing long enough to use it. Some calculations suggest you'd need the energy equivalent of a stellar mass to create even a small wormhole. Humanity's total energy production throughout all of history wouldn't be enough to cover the down payment. And then there's the question of where the wormhole would go. Even in theory, we have no idea how to direct a wormhole to a specific destination, let alone to a parallel universe, which might not even be a meaningful destination in the mathematical sense. The other bubble universes of eternal inflation aren't located somewhere we could point a wormhole toward. They're in regions of space-time that are fundamentally disconnected from ours. The branching worlds of many worlds quantum mechanics aren't in different places at all. They're different configurations of reality in the same mathematical space. It's not clear that a wormhole could connect to them even in principle. Some theorists have speculated about more exotic connections. If our universe is a brain floating in a higher dimensional bulk, maybe wormholes could punch through the bulk and emerge on a different brain, a different universe with different physics. But this is speculation piled on top of speculation, mathematics without any observational grounding. It's fun to think about, but it's nowhere near something we could engineer or even detect. The bottom line is this: wormholes are mathematically fascinating, but almost certainly not practical. They might not exist at all. If they exist, they're probably unstable. If they're stable, we'd need exotic matter we can't produce. If we could produce it, we'd need engineering capabilities far beyond anything imaginable. And even then, we might not be able to reach other universes anyway. The multiverse, if it exists, is probably forever beyond our reach. We can contemplate it, model it, even search for indirect evidence of it. But actually visiting another universe is a fantasy that physics seems determined to keep fictional. That said, never say never. A century ago, human flight was barely established, and space travel was pure fantasy. Our understanding of physics has grown enormously, and it will continue to grow. Maybe some future breakthrough will reveal possibilities we can't imagine today. Maybe there's a loophole in the laws of physics that allows for inter-universe travel without the problems we've identified. Science has surprised us before. But based on everything we currently know, the parallel universes, if they exist, are places we can dream about, think about, and wonder about, but never actually visit. The good news? Dreaming, thinking, and wondering are pretty amazing things to do, and they don't require a single gram of exotic matter. We've come a long way together. We started with ancient Greek philosophers staring at the Mediterranean sky, wondering if our world was the only one. We traced the idea of multiple universes through centuries of religious persecution, scientific revolution, and mathematical discovery. We explored the infinite expanse of space that guarantees cosmic duplicates, the bubble universes of eternal inflation, the branching realities of quantum mechanics, the hidden dimensions of string theory, and the vast landscape of 10 to the 500 possible physical laws. We visited CERN and its particle-smashing detectors, listened to critics who question whether any of this is science, and reluctantly admitted that wormholes probably won't be taking us anywhere anytime soon. Now it's time to step back and ask, what does it all mean? If the multiverse is real, or even if it's just a serious scientific possibility, how should that change the way we think about ourselves, our universe, and our place in existence? Let's start with what we know for certain, which, admittedly, isn't much. We know that the universe is vast beyond comprehension. We know that it operates according to mathematical laws that humans have been remarkably successful at discovering. We know that those laws allow for extraordinary possibilities: black holes, neutron stars, the expansion of space itself. And we know that our best current theories, taken seriously, point toward the existence of other universes beyond our own. This isn't proof, it isn't certainty, but it's not nothing either. The multiverse has gone from philosophical speculation to a legitimate scientific hypothesis supported by theoretical frameworks that have been tested in other domains. We're not just dreaming anymore, we're calculating. The implications, if the multiverse is real, are staggering. Consider the Level 1 multiverse, the infinite space beyond our cosmic horizon where, by mathematical necessity, every possible configuration of matter occurs. Somewhere out there, inconceivably far away, there's an exact copy of you living an exactly identical life. But there's also a copy that made different choices. A copy that never existed because your parents never met. A copy living in a world where history unfolded completely differently. Every story that could be written is being lived somewhere. Every path not taken is being walked by some version of you. It's like being told that the library of all possible books exists, and your life is just one volume among infinite shelves. The quantum multiverse, if the many worlds interpretation is correct, is even more intimate. It's not just that copies of you exist far away in space. It's that you're constantly splitting into multiple versions of yourself, right here, right now, with every quantum event in your body and brain. The you who started reading this sentence has already branched into countless versions who will finish it with slightly different neural states. By the time you reach the end of this paragraph, you will have fragmented into more copies than there are atoms in the observable universe. Not in some distant realm, but in parallel branches of reality that share your past but diverge infinitely into different futures. If that doesn't make you pause and stare at the wall for a moment, you might not be fully grasping what's being proposed. And then there's the string landscape, suggesting that the very laws of physics are not unique, that our universe's specific set of particles, forces, and constants is just one configuration among 10 to the 500 alternatives. Other universes might have completely different rules, different chemistry, different possibilities for structure and life. Some might be dead and cold, incapable of forming anything interesting. Others might have complexities we can't imagine, life forms we couldn't recognize, beauty we couldn't appreciate. The multiverse, in this view, is not just a collection of different stories in the same genre. It's every genre imaginable, including genres that don't translate into any human concept. What does this mean for human significance? This is where people tend to have strong reactions, and those reactions say a lot about their underlying worldview. For some, the multiverse is deeply humbling. We already knew we weren't at the center of the solar system, or the galaxy, or the universe. But at least we thought our universe was special, the one and only stage on which the cosmic drama played out. The multiverse says, not even that. Our universe is one bubble among infinite bubbles, one branch among infinite branches, one configuration among infinite configurations. We're not special. We're not unique. We're just one instance of a pattern that repeats endlessly, variations on a theme that has no composer and no audience. For others, the multiverse is strangely liberating. If every possible version of you exists somewhere, then, in a sense, you can't fail. Somewhere, you succeeded at everything you ever attempted. Somewhere, you made the right choice at every fork in the road. Somewhere, you're living your best possible life. Of course, somewhere you're also living your worst possible life, which is less comforting. But the point is that the weight of individual choices feels different when you know that all choices are made by some version of you. You're not selecting from possibilities and eliminating the others. You're just navigating to one particular branch while other versions of you navigate to all the others. It's a strange kind of freedom, or maybe a strange kind of determinism, depending on how you look at it. And for still others, the multiverse changes nothing about what matters. Yes, there might be infinite copies of you. Yes, your universe might be one among countless others. But so what? You still have to live your life. You still experience joy and suffering, love and loss, hope and fear. The existence of other versions of you doesn't diminish the reality of your experience. If anything, it might enhance it. Knowing that your particular configuration of atoms, your particular sequence of experiences, your particular consciousness is unique in its exact details, even if not in its general type. You are the only you that is precisely you, even if approximate yous are scattered across the multiverse. That might be enough. The philosophical questions raised by the multiverse are ancient ones in new clothing. What is personal identity? What is free will? What is meaning? Philosophers have debated these for millennia without the multiverse. And the multiverse doesn't resolve the debates, it just adds new dimensions to them. If you believe that meaning comes from uniqueness, the multiverse is a challenge. If you believe that meaning comes from experience, the multiverse is irrelevant. If you believe that meaning is something we create rather than discover, then the multiverse is just another fascinating fact about reality. No more threatening to meaning than the size of the observable universe or the indifference of natural selection. What about the future of multiverse research? Despite the skeptics' objections, the scientific investigation of the multiverse is very much alive. Future experiments at particle colliders might reveal signs of supersymmetry or extra dimensions, providing indirect support for string theory and its landscape. More precise measurements of the cosmic microwave background might detect signatures of bubble collisions or other anomalies that could point to other universes. Advances in quantum computing and quantum information theory might shed light on the foundations of quantum mechanics and whether many worlds is the correct interpretation. We're not done exploring. We've barely started. New telescopes and observatories are coming online that will map the universe with unprecedented precision. The James Webb Space Telescope is already revolutionizing our understanding of the early cosmos. Future gravitational wave detectors might pick up signals from the very first moments after the Big Bang, when inflationary dynamics were at play. The Simons Observatory and CMBS-4 will probe the polarization of the cosmic microwave background with exquisite sensitivity, potentially revealing signatures of primordial gravitational waves that could confirm or constrain inflationary models. Each of these experiments is a chance to learn something new, maybe something that supports the multiverse, maybe something that rules out certain versions of it, maybe something completely unexpected that forces us to rethink everything. Theoretical physics, too, continues to evolve. String theory might give way to a deeper framework that either embraces or eliminates the landscape. New approaches to quantum gravity might resolve the puzzles that currently lead to multiverse conclusions. The history of physics is full of paradigm shifts where seemingly intractable problems were dissolved by new conceptual frameworks. Maybe the multiverse is the final answer, the ultimate structure of reality. Or maybe it's a stepping stone to something even stranger, something we can't currently imagine. The only way to find out is to keep doing the work. Keep calculating, keep observing, keep questioning. There's something beautiful about the position we find ourselves in. Humans evolved on a small planet orbiting an ordinary star in an unremarkable galaxy. We developed brains capable of abstract thought, languages capable of conveying ideas across generations, and scientific methods capable of probing the deepest structures of reality. And now, using those tools, we've arrived at theories suggesting that reality might be infinitely larger and stranger than anything our ancestors imagined. The universe isn't just bigger than we thought. It might be everything that could possibly be, all at once, forever. And we figured that out, or at least seriously proposed it, using nothing but our minds and our instruments and our relentless curiosity. Whether the multiverse is ultimately confirmed or refuted, the journey of discovery has value in itself. We've learned to think bigger, to question assumptions, to follow mathematics wherever it leads, even when it leads to uncomfortable places. We've learned that the universe doesn't owe us simplicity or comprehensibility, and that our intuitions, shaped by survival on an African savanna, are not reliable guides to physics at cosmic or quantum scales. We've learned humility, the kind of humility that comes from realizing how much we don't know and how much there might be that we can never know. So here's where we leave things. The multiverse might be real. If it is, you are not unique. Not in the sense of being the only version of yourself anyway. But you are still you, the particular you having this particular experience at this particular moment. And that moment is real, regardless of how many other moments exist in how many other universes. The map of reality has expanded beyond recognition, from a single cosmos to an infinite ensemble of cosmoses, each as real as ours. It's a lot to take in. It might take humanity generations to fully absorb what it means, if it's true. Or it might turn out to be a beautiful but mistaken detour, a path not taken in the branching history of science. Either way, the question that started our journey remains as powerful as ever. What if you're not the only version of yourself? Ancient philosophers asked it. Medieval heretics died for it. Modern physicists are calculating probabilities about it. And you, watching this video, are now part of that long tradition of humans looking up at the sky and wondering if there's more out there than we can see. There probably is. There might be everything. And even if we never know for certain, the asking is its own reward. Thanks for joining me on this journey through the multiverse. If you made it this far, you're clearly someone who enjoys having their mind blown by the biggest questions in science. Hit that subscribe button if you want more content like this. Leave a comment telling me which version of the multiverse you find most compelling or most terrifying, and share this video with someone who needs to question their assumptions about reality. Until next time, remember, somewhere in the multiverse, there's a version of you who already subscribed. Don't let them be the only one. And if you're lying awake tonight, staring at the ceiling, wondering about all those other versions of yourself out there in the infinite expanse of reality, well, take comfort in this. They're probably lying awake too, wondering about you. In the multiverse, nobody has to wonder alone. Sweet dreams, and see you in the next one.